In our last screencast, we learned how free-falling objects behave. In this screencast, we are going to consider more cases of free fall. We'll begin with a review of objects that are dropped. Then we'll consider some where they are thrown downward with an initial velocity. Then we will consider some where they have been thrown upward with an initial velocity. And then we'll just consider a simple case of being thrown from the ground upward and downward. Now I just want to make a quick comment about these two depictions. You'll notice the symmetry of heights on the way up and on the way down in both of these last two examples. This is a fundamental characteristic of projectiles launched upwards. There is a pronounced symmetry on the way up and on the way down. If these balls are truly thrown directly upward, when they came down they would be directly on top of each other. So you would only see one path coming down. So the way artists typically depict this is to show that shifted just a little bit forward, but what they really intend is that the ball goes upward and downward in exactly the same path. They're trying to indicate the symmetry. So let us begin with a review of the first case, a free fall object from rest. We have a cliff. It's 100 meters tall. And in the previous screencast, we considered both cases when we set up our reference frame. So in this particular case, I've set up the reference frame as the cliff being at 0 and the bottom of the cliff being at -100. So two typical questions: when will it hit the ground and what will its impact velocity be? Well, let's begin with making a sketch of our velocity time graph. So we have velocity time. At the instant it's dropped, the velocity is 0. But we can see in the direction that it's moving, it's negative. It's moving in a negative direction. So that means the velocity is negative. Let's recount what we know about velocity time graphs. We can read velocity time. The gradient tells us is delta v over delta t, which is the acceleration, and the area is delta v times t, which is the displacement, delta y. So if the gradient is acceleration, we know this is accelerating because of gravity. And we know that value is approximately 10 in magnitude, and the direction with this reference frame is negative. So we're looking at a constant slope of -10. Every 1 second, the velocity changes by 10 meters per second. Now let us consider the position, y versus t, and what we can tell from a position time graph. We can read the position y and time. The gradient is delta y over delta t, which is the velocity. And the area is y delta y times t, which we said is meters times seconds. Meters seconds is nothing. So the area has no particular meaning. Now when we consider the position at time 0, it is at a position of 0. So we are again here. But notice immediately the position is negative. So we are talking about quadrant 4 for all the plots, all the points right here. And as you recall from the last screencast, during the first time interval, it's traveling slowly, so it covers a smaller distance. And with each successive time interval, it is traveling faster, so it covers a greater distance. So that produces the downward cupping parabola that we've seen before. So those are our sketch graphs. Now let us write the models for these two projectiles. First, let's do the velocity. We always want to start with the velocity. Velocity equals at plus v0, and we know the acceleration is -9.81 times time, and the initial velocity is 0. So this is our model for the velocity. Now let us write the model for position. Y equals 1/2 at squared plus v0t plus y0. So we have y equals 1/2 times -9.81 t squared. It's dropped, so the initial velocity is 0, and this term drops out, and the initial position is 0. So this term drops out. So we are left with a model of negative 4.905 t squared. And a reminder, we don't round until the end, so we would preserve this value. So these are our two models. Now, going back to our original questions, when will it hit the ground? What will its impact velocity be? Well, when it hits the ground, the position will be minus 100. So when will the position be minus 100? We substitute that in. Divide both sides by 4.905, negative 4.905. That's going to be t squared. And that gives us a t squared value equal to 20.38736. And then we want the square root of that. And that gives us a time of 4.51524 seconds unrounded. We go back to our initial values. We have 100. In this case, we're lacking a little bit of clarity about the number of significant digits. And we used three significant digits for 9.81. And so for this case, let's go to 3 significant digits. So t will be 4.52 seconds. Now the velocity, in this particular case, we will use that time. So v equals negative 9.81 times the unrounded value of the time, the 20.38736. Or excuse me, the 4.52. The unrounded 4.51524. Which gives us a velocity of 44.29447. So again, we're relegated to 3 significant digits. That's these 3. So the velocity then is 44.3 meters per second. So this is a review of what we covered in the last screencast. We're going to repeat these steps for each of the other cases. First, I want to review how we would use the average velocity table to solve this. Remember, for the average velocity table, that the displacement, delta y, is equal to the average velocity multiplied by the time. Now we're doing a quick calculation in this case, but we could use specific values, but just to show you how quickly this could be done. At time 0, the velocity is, again, this should be 0, 1, 2, 3, 4. At time 0, the velocity is 0. At time 1, the velocity is 10. So that means that the average velocity is 5. And so delta y is average velocity times time, or 5 meters. After 2 seconds, the velocity is 20, the average velocity is 10, and we have a displacement of 20 meters. After time 3, it's 30, and the average velocity then would be 15, and the displacement 15 times 3 would give 45. Now we have an average speed of 40, or excuse me, an instantaneous velocity of 40, an average of 20, and that would give us a displacement of 80. And then after 5 seconds, we have a velocity of 50, an average velocity of 25, and that would mean that the displacement would be 125 meters. So what we have just demonstrated, and we didn't have to solve them all, is that the answer lies between 4 and 5 seconds. So this is a powerful technique for multiple choice questions or to get a ballpark order of magnitude estimate. And this type of solution will always work, nearly always work on a multiple choice question, both on the IB exam and on the SAT2 and on the Regents exam. So that was our first case. Now let us consider free fall with downward velocity. So we have a ball that's thrown downward with a speed of 8 meters per second from the edge of the same cliff. When will it hit the ground? So if we remember in our last case, the ball hit in 4.52 seconds. So in the case where it was dropped, it was 4.52 seconds. Now you might expect then, we make a prediction that if you're throwing it downward, it should land more quickly. And this is a great way to check your answers, to come up with a conceptual estimate to begin with. Now let's talk a little bit about reference frame. You notice we've set this as 0, the cliff height is 0. Now I'm defining the cliff height in this case as the release height of the hand. We could make this more complicated by being dropped right at the cliff height or at the height of the hand, or if the ball's being thrown upward, maybe the release height is here. We're going to treat these all the same for simplicity's sake. We don't need to get that complicated, but those are just a minor correction, because a drop from the cliff right here at the edge that were rolled off the edge would be 100. This would be about 101, and this would be about 102. But we're not going to make those kind of corrections in this example because we want to show the process. All right, so notice our coordinate system here. I put the number line here to remind us of our coordinate system. We have negatives in this particular case. So what we know is we have a V0 has a magnitude of 8 meters per second, but it's in this direction, so the initial velocity is negative 8. So when we make our VT graph, like so, again, we can read V and T, the gradient is acceleration and the area is the displacement. Our initial velocity is going to be minus 8, like so. And then it's going to increase by minus 10 every second. So minus 8, minus 18, and so on. The gradient of this graph is negative 10 meters per second squared. And now when we look at the displacement, y versus t, we can read y and t, and the gradient gives us the velocity, and the area tells us nothing. Well, let's see, where does the position start? The position starts at 0. And this one is also going to be a downward cropping parabola. As we can see, as it goes downward, it is going to, again, increase, and each distance increment would be even greater than the one before it. However, it has an initial speed. So what we might expect is, whereas the last case, the parabola had a shape like this, we would expect this parabola to be tighter. We expect it to get to minus 100 sooner. So this is the throw, and this is the drop, like so. Now it's time for us to write our models. We go to the velocity. V equals AT plus V0. We have V of negative 9.81 t. And now we have an initial velocity of minus 8. This is our model. Next, we go to the y. Y equals 1/2 AT squared plus V0t plus Y0. So we have y equals 1/2 negative 9.81 t squared, and now we have initial velocity of negative 8, minus 8t, and the initial position is 0. So we have y equals negative 4.905 t squared minus 8t is the model for the position. Now just as before we wanted to solve this equation, we know the y is going to equal minus 100. And that then is negative 4.905 t squared minus 8t. So this presents a little bit of a problem here because this isn't just a simple divisor. Here, it's more complicated. Now we represent this as a quadratic. So we could in this case solve this and say 0 equals negative 4.905 t squared minus 8t plus 100, and then use the quadratic formula to solve it. complicated, tiresome, difficult. So we are going to go use a different approach. What we actually have in this case, if we're thinking of this as functions, is we have the equation of the position of the projectile, which is what we're calling y. And we can, so we have the equation of the position, which is y. And we have the position, in that equation, y of the projectile is negative 4.905 t squared minus 8t. But we also have the equation of the ground, which is a static minus 100. Well, we want to know when this equals this. Solving them algebraically, we've already said, involves the quadratic formula, but we can solve these graphically. We can do this on our graphing calculator very, very quickly. And that's what I will demonstrate next, how to solve that on our graphing calculator. So now that we have our models for velocity and the position in particular is what we're concerned about, we can graph them. So we had the position of the projectile, which we can enter as negative 4.905 x squared minus 8x. So that's the equation of the projectile. And now we have the equation of the ground, which is negative 100. Now we want to graph these things. And let me make sure my statistical plots are off. And they need to be off. And let me check that again, make sure. Okay, great. So now I go to y equal. I got y equals. Those are my functions. And now I'm going to make my graph. But before I make the graph, I've got to set my window. So my x, we're going to start at a time. X is time, so we'll start at 0. And an x max, how long is this going to take? Well, we knew the last one was 4.5 seconds. So we know this is going to take less, but let's set it equal to 5 seconds. Our y min, the ground is at 100. So let's make it a little bit lower so we can actually see it. So let's make it maybe 120. And the y max was 0 at the top of the cliff. Let's make that a little higher and make that negative 10. Excuse me, positive 10. And the y min needs to be negative 120. And now we graph these things. Let me see where my error is. Aha, that's supposed to be times. 4.905 x squared, and now we graph. And so we can see the blue curve is the position time of the projectile, and this is the position time of the ground. You notice it's not changing. But when they what this intersection here means that they are occupying the same position. They have the same y value. So what we want is to calculate the intersection. So that's second trace, which is calculate. We want the intersection. And is this the first curve? Yes. So I select yes. I notice the flashing X on the blue curve. And then I notice the flashing X on the red curve. Yes. It asks me, do we want to guess what the time is? There's no real reason for that. I almost always just click through it. And what it says now is that the intersection, the time is 3.7727 at a position of minus 100. Now this time of 3.77 is what we predicted. It should be less than 4.55. So what we just saw with the graphing calculator is that we can very, very quickly, if we know how to use that as a tool, use it to get us the intersection. So what do we write on our paper for solution here? Well, we're looking, what we say is, the quadratic formula was an option. We're not going to write quadratic formula in our answer, but we can write that the position of the projectile is this, the position of the ground is this, so we're looking for when yp equals yg, And we can do, we can take a note, graphing calculator intersection. And we can record the values that came up on our screen. T equals 3.7727,941 seconds, where y equals negative 100. So then it becomes a simple matter, and well, we can first record with our 3 significant digits our answer, boxed form. Time equals 3.77 seconds. And then we use the unrounded form to find the velocity, the impact velocity, which we expect to be greater. In the prior example, the impact velocity was 44.3 meters per second. So we had 4.52 seconds, we had 44.3 meters per second. Stands to reason that the projectile will hit the ground with a higher velocity when it's thrown downward. That's a common sense thing. So now we have v equals negative 9.81 times the unrounded value of 3.7727,941. Now again, what I would do with these values is store them in the calculator as a variable. In this particular case, because it came from the intersection, we would need to write it down. But in other cases, when it's on our screen, we would store it, as I showed you to do that systematically in the past. Oh, and minus 8. So we have negative 9.81 times 3.7727,941 minus 8. And we get negative 45.01. So that would give us then an impact velocity of negative 45.0 meters per second to the minus 1 with significant digits. Now, of course, we might also want to express it in scientific notation, but this is more about the process at this point. So our predictions held. It is traveling more quickly. But notice it only gets there less than 0.8 seconds faster. And so its speed is not all that much faster because the time interval is so slow. And if you were to think about it, a tenth of a second, if the object is accelerating at 10 meters per second every second, in 1 second it would only increase by 10. In this particular case, it's not even a tenth of a second. So we might expect that it would increase by less than 1 meter per second, and that's what we see. This conceptual thing we do at the end, where we try to make sense of the values related to the graph and the prediction and the differences, is integral to checking your work and understanding physics. So that was our second case, free fall with downward velocity. Now let's take a look at the average velocity table. And like the last time, my numbers are a little askew here. So we have 0, 1, 2, 3. Again, displacement, delta y, equals average velocity times the time. So at time 0, the velocity is minus 8. There is a difference. At time 1, the velocity is minus 18 because in 1 second the speed increases by 10. The velocity increases by negative 10. So in this case, the average velocity is minus 13. So the delta y is minus 13 meters after 1 second. So now we have minus 28, and the average, negative 8 plus a negative 28 is negative 36, divided by 2 is negative 18. 18 times 2, minus 36. And now we have minus 38, and minus 8 adds up to negative 46, divided by 2 is minus 23. Notice, just as in the previous examples, the average velocity is increasing by 5. Why? Because the velocity is increasing by 10 and we're dividing it by 2. So minus 23 times 3 is minus 69. And at 4 seconds, we have minus 48. 48 and 8 is minus 56, which gives us minus 28. And minus 28 times 4 is minus 112. So again, we can see very clearly there is a case that the time is between 3 and 4 seconds, that the displacement will reach 100, the velocity will be somewhere between 38 and 48, and this gives us a ballpark order of magnitude estimate using the average velocity table method. So now it's time to consider the most complicated case we're going to get in today's screencast. Free fall with upward velocity. So same situation we've been considering, except the difference is this time the fellow is throwing it upward. So if we look at this particular case, it's going to go upward and then come down. We would expect then that the time would be greater than if we just dropped it. And if we had just dropped it, we expect the time to be greater than 4.52 seconds. The velocity, if you notice, it is falling from a greater height. So that means it's going to have more time to hit the ground and to accelerate as it moves toward hitting the ground. So therefore, we would expect the velocity to be greater than the 44.3 we got in the first case. So now we need to pay attention to our reference frame here very carefully. We know the acceleration is downward. Acceleration is negative 9.81 meters per second squared. But the velocity is in this direction. So the V0 is positive 8 meters per second. So now we go to make our VT graph. Again, what we can read is velocity time. The gradient is delta V over delta T, which is acceleration. The area is delta V times T, which is the displacement. And we're now starting out with a positive velocity of 8 meters per second. Now let's think about this. Just from the picture, we can see it's covering less distance, which means its average velocity is less. And when it reaches the top, the velocity is 0. The acceleration is gravity, negative 9.81. So we would expect then this to have a negative slope, as we've seen before. It has a constant acceleration, a constant negative slope of minus 10. Notice all that's happened in the three cases that we've considered is the velocity time graph has been shifted along, the intercept has been shifted. When it was dropped, it was 0. When it was thrown downward, it was here. When it was thrown upward, it was here. But they were parallel because they have the same slope. Now let us consider the velocity, or the displacement time. Now again, just like in the other cases, we have had a position of 0 as our initial position. But notice if this is the initial position of 0, it goes up well above, it goes well up above into the positive area and then comes down. So we are going to have another downward cupped parabola. Another downward cupped parabola. But it's going to go into positive territory, and this here represents the peak. So now let us write our models. V equals AT plus V0. Acceleration, negative 9.81 t, and the initial velocity is plus 8. Remember in the last case it was minus 8. So there is our model. Now in this particular case, for position, we have y equals 1/2 at squared plus v0t plus y0. And the acceleration is negative 9.81. The v0 is plus 8, and the initial position we've set at 0. So we have a model of y equals negative 4.905 t squared plus 8t. When will it hit the ground? What will its impact velocity be? Well, let's see. We can't simply solve this for y equals minus 100 again. So now we're going to go about solving this exactly the same way we did before. We want to know when there's an intersection. Y of the projectile is negative 4.905 t squared. Y of the ground is negative 100. So this is where we're going to go back into our graphing calculator and solve it that way. So from the last example, we can see our graph up on the screen, and we need to make some modifications. And so the modifications are going to be to the functions of the position of the object and the window that we can see. So we look at y equal, the position of the objects, yes, it's negative 4.905 t squared, but it's not minus 8x, it's plus 8x. So we change that minus to a plus. And the ground still has the same equation. Next, we need to adjust the window. Now, we know the time is going to x is times. We'll start at 0, but we're not exactly sure. We know it's going to take longer. So why don't we let it go to maybe 10 seconds? We may reset it, if that's the case. So now we look at our y position. Minus 120, that was set for the ground, that's fine. But the y max in the positive direction, we don't really know. So let's make it perhaps 40. And now we graph, and we can see it perfectly. Notice it goes above 0, comes back down, and we have this intersection right here where the red and blue meet. So now it's second trace for the calculate. The intersection, first curve, yes. Second curve, yes. Estimate, nah, I don't need to. And the intersection, 5.403. And we predicted it would be longer than the 4.5, and indeed it is longer. And the correct position at minus 100. So I've already recorded that I solved this with the graphing calculator intersection. I've recorded the unrounded time, and now I'll record the rounded time. 3 significant digits will be 5.40 seconds. And we predicted in the beginning it would be longer than 4.52. So that's perfect. Now it's time to compute the velocity, the impact velocity. Equals negative 9.81 times the unrounded value, 5.403, t plus 8. And when we plug this into our calculators, we get a surprising negative 45.01111 meters per second. To 3 significant digits, negative 45.0 meters per second. This is exactly the same velocity, impact velocity, as the case where it was thrown downward. To 7 significant digits. It's exactly the same. That's counterintuitive. Let's see if we can make sense of why that would be. Well, if we consider at this moment in time, the velocity is plus 8 meters per second. But when it's returning downward, its velocity is minus 8 meters per second. So what goes up must come down, and we have this symmetry. If these time intervals are equal and these distances are equal, then the velocities are equal. So when this reaches the 0 point from where it was launched, it's going to have the same speed as if it had been thrown down. All we've done is added this part of the trajectory. So what we can see is, in fact, the time, or the impact velocity, will be exactly the same. It just takes longer because it has to make that upward path. Not at all intuitive. Now let's solve this using our average velocity table. Again, we'll make corrections for the times. We know it's between 5 and 6 seconds. So 0, 1, 2, 3, 4, 5, 6. Now, usually we don't know this a priori, the answer. But what I'm trying to show you is if you do this row by row going down, you can save yourself work. So our initial velocity is plus 8. After 1 second, it's minus 2. 8 plus a negative 10 is minus 2. So our average velocity at this time is 8 plus a negative 2 is 6 divided by 2 is 3. So the displacement in this case is 3 meters. It's above the launch point by 3 meters. The next moment, the velocity is minus 12. And so then we have 8 and negative 12 gives us negative 4 divided by 2 is minus 2. And so negative 2 times 12 is minus 4. So in other words, what this is saying is that in the first second, the velocity goes from being positive to negative. The direction changes. So that means in the first second, we've already passed the peak in the first second because the velocity is minus 2. The displacement is plus 3. 0 plus 3, but it's already on its way down. That's what that means. So this one is tricky to interpret, but if we use pictures, it can help us sort it out. Now we go to minus 22. Minus 22 gives us minus 14 over 2 is minus 7. And then we have negative 7 times 3 is minus 21. Minus 32. This becomes minus 12. Minus 48. Minus 42. Minus 17. Minus 17 times 5 is minus 85. And then we have minus 52, which gives us minus 22 average velocity. And that's 100 and minus 146, I believe. 120, no, 132. Minus 132. Minus 132 meters. So what we see is the impact should be between 5 and 6, and the impact velocity should be between 42 and 52. But this will, again, allow us to answer any multiple choice question rather quickly. Our final case is the case of a projectile launched upward from the ground. Now, we've already covered most of the main elements. Let's first examine the reference frame. We're now setting the ground equal to 0. We have an initial launch, and in this case, let's make it something interesting like, say, positive 40 meters per second, the initial velocity. What we know is with each second, its speed is going to decrease. So if this represents 1 second, this then will be 30 meters per second. This will be 20, this will be 10, and it will be 0. And then from 0, this will become minus 10, minus 20, minus 30, minus 40. Notice the launch velocity is equal to the impact velocity, the return velocity, and we have this symmetry of speeds and displacements on the way up and on the way down. So let's look at our velocity time graph. We have V, what we can read is velocity in time, the gradient is the acceleration, and the area is the displacement. So we're starting out in this case with a positive velocity of 50. And what happens to that velocity? It decreases over a period of 40, our initial velocity, a period of 1, 2, 3, 4 seconds, it decreases to 0. And then notice it shifts to the negative and becomes minus 40. This point here is at the top. This graph is one of the most non-intuitive graphs in the whole course. So that's why we're paying a lot of attention to this velocity time graph. This is an object thrown upwards and downward. Positive velocity that gets smaller and smaller reaches 0 and then increases in speed as it's returning in the opposite direction. Our displacement graph in this particular case. We start at a position of 0, and its speed starts out very fast. Remember, we can read displacement in time. The gradient is the velocity, and the area tells us nothing. So if the gradient is the highest here, we're looking at a steep curve that becomes flatter and eventually reaches a peak where the slope is 0 and comes downward, and it returns to a position of 0. Note, at this point up here, the gradient equals 0, and that's the velocity. Notice everywhere in this direction, the gradient is positive, and in this side, the gradient is negative. What I did not depict well in this drawing is that these are perfectly symmetrical. They're symmetrical halves. And this line of symmetry that runs through it splits the time. If we call this time A and this time B, time A equals time B. So there is this symmetry of time. It takes just as much time to fall from the peak and come downward as it does to go from the launch to the peak. So there is this symmetry. And of course, this is true for negligible air resistance. Symmetry. Very powerful. All right, so now when we write our models, we have our velocity, which is AT plus V0. We have negative 9.81 t, and the initial velocity is plus 40. There's our model. For our position, y equals 1/2 AT squared plus V0t plus Y0, negative 9.81 t squared. Initial velocity is 40t, initial position is 0. So we have y equals negative 4.905 t squared plus 40t. So those are our two models. Now again, I would remind you from the first lesson on projectiles, I showed you how to model these in small increments of time with spreadsheet. And also, once we have these in our graphing calculator, we can evaluate them in the table, and that's a very valuable tool for us. So now let's consider, we want to actually find out how long it will take to hit the ground, come back down, and what its impact velocity will be. Well, we know in this particular case that the position will be 0 when that happens. So we have negative 4.905 t squared plus 40t. Now in this particular case of it being 0, we could factor a t. So 0 equals t times negative 4.905 t plus 40. That's so massive. 0 equals t times negative 4.905 t plus 40. Dividing both sides by t, we get negative 4.905 t plus 40, and now we have 4.905 t equals 40, and t equals 40 divided by 4.905, which is 8.15494 seconds. With 3 significant digits, we're left with 8.15 seconds. Now we could just as easily use our graphing calculator method on this, and we'll quickly do that. So from our prior example, we have the results here, and again we need to change our functions. So we have the position of this object is negative 4.905 t squared plus 40x. plus 40. Oops. Plus 40x. And we don't want the y2 to be negative 100. We want it to return to the ground, which is just 0. Now we need to adjust our window. Our time from 0, we calculated 8.15 seconds, so 10 seconds should give us enough. The y-axis, the y-min, our lowest point is 0, so maybe we'll make this minus 10. And we don't really know how high it's going to get, so let's make it maybe 80. And let's graph. So we can see the y equals 0, and we have our parabola like so. So now it's time to calculate the intersection. .154939, which is exactly what we got when we calculated it algebraically. So we have a test there with the calculator. So we confirmed our value of the time from the graphing calculator intersection. What this means, incidentally, is that this time here is 4.075 seconds to the top and 4.075 seconds downward. That's the total time in the air divided by 2. That's important to remember. So now we put in our time, negative 9.81 times 8.1549 plus 40. And we get an answer of 0. Which, of course, after the object hits the ground and comes to a stop, the answer wasn't 0. The answer was negative 40 meters per second. But I was anticipating talking about the misconception. The misconception is, what's the velocity when it hits the ground? Students want to say it's 0. Yes, that's true after it's come to a stop. But when we ask about the impact velocity, we're talking about the velocity at the instant before impact. And what we've seen all along is this symmetry. Plus 40 and negative 40 upon impact. So the calculation actually bears out and supports exactly what we would have expected. So you might be asking, how would we use the average velocity table to solve this? Well, let's give it a try. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have our velocity, which is 40, and it decreases 30, 20, 10, 0, negative 10, negative 20, negative 30, negative 40, negative 50. The average velocity at this point is 35, and then 30, 10 and 40 is 50, divided by 2 is 25. We can see it's decreasing by 5, so 20, 15, 10, 5, 0, minus 5. So the displacement is equal to the average velocity times the time. So 35 times 1 is 35. So what does that mean? In that time, it traveled up 35 meters. Now we have 30 times 2, which is 60. So you saw in the first second it went 35, and the next one it's only going 25. 25 times 3 is 75. And here we have 20 times 4 is 80. And then 15 times 5 is 45. 10 times 6 is 60. 15 times 5 is 75, excuse me. And 5 times 7, 35. 0 times 8 is 0. And this would be negative 45. So what do we see here? We see 35, 60, 75, 80, 75. Notice that these two values are paired. So we've got symmetry. These two values are paired. These two values are paired. And these two values are paired. So this average velocity table here can allow us to approximate where the apex is and the total time. We know, in this case, it's 8 because it worked out perfectly. That it won't always do that. In this particular case, they were very good numbers and worked easily for us.